In this lecture, we continue our discussion on superconductivity. In an earlier lecture, we have already discussed various aspects of superconductivity, its definition, the different parameters like the critical current density, the critical temperature, the critical magnetic field and so on. We have also discussed the two varieties of superconductors. One is called the type 1 and there is type 2 superconductors. So, let me try to repeat few of the things which we have earlier discussed. These are the two diagrams we discussed last time. This is the type 1 superconductor, the characteristics of type 1 superconductor so far as the magnetization versus magnetic field is concerned. There is an abrupt change of magnetization and the superconductivity is lost at a particular value of magnetic field, which is known as the Hc. Whereas, in type 2 superconductors, this diagram has been corrected now. This was earlier written as type 1, but actually it will be type 2 superconductors and there will be Hc2. So, we have two different critical field strengths, one is Hc1 and there is Hc2. So, beyond Hc1 there is no abrupt change in the characteristics of the material. It does not change suddenly or immediately to a normal state of material from superconducting state. Instead, there is a gradual change. So, we have a dual phase which is known as the vortex region. So, slowly from in a superconducting state there is no flux penetration, whereas in the normal state there is a complete flux penetration, whereas in the vortex phase or the vortex state there is a limited amount of flux penetration, and as the magnetic field increases more and more flux lines penetrated, and finally at a level at a value of Hc2 the complete penetration takes place and the superconductor is converted to a normal material, that means it is no longer a superconductor. So, that we have earlier discussed. We have also discussed that the type 2 superconductors carry much larger current, the current density, the critical current density is much higher in case of type 2 superconductors, and therefore, they have a great practical importance. Also, there is another advantage of the type 2 superconductors, since there is no sudden change from superconducting state to the non superconducting state, there is a gradual change. So, there is no catastrophic failure of the material so far as the magnetic field is concerned or the current density is concerned, and therefore, it is more preferred whenever we are talking about any practical device. Hc2, that is the second or the high field critical magnetic field, strongly depends on the microstructure of the material. So, it is not the intrinsic property of the material, one can play with it from the way the material is prepared and how the material is processed and so on. So, particularly in presence of pinning center, if you can somehow introduce some pinning centers which actually acts as a barrier to the flux penetration through the material, then the value of Hc2 can be extended and the zone of useful zone of magnetic field enhances. So, you have a better material. So, by introducing different kind of pinning centers, one can really increase the Hc2 value. What are the pinning centers? This also we briefly discussed. There are three varieties of pinning centers one can think of. One is the dislocations. So, dislocations, as you have discussed previously in connection with the defect structure of the material, these are crystalline defects. So, all crystalline materials are supposed to have some dislocations, and dislocations are basic defects which can control the plastic property mechanical deformation, plastic mechanical deformation of the of any material. Both elements or metals or intermetallics, they have a certain amount of elastic deformation beyond the elastic limit. In fact, in case of metals it is much more, whereas intermetallic compounds is a little harder and relatively brittle. However, even then one can cold work it. Cold work is nothing but it is a metallurgical term basically. It is basically deformation, plastic, allowing the material to deform plastically under high pressure. So, by deforming you can introduce dislocations, and as you deform more and more dislocations gets generated. So, the dislocations becomes difficult from the difficult for the lines of magnetic lines of force or flux lines to penetrate through this dislocation barrier. So, that acts as a pinning center. Then you have another kind of defects in the crystal, particularly in polycrystalline material. It may not be there in the single crystal, but in polycrystalline material it is certain invariably will be there. So, it is the junction between or the boundary between the two neighboring crystals, and that is a two dimensional boundary. So, these boundaries also act pinning centers. So, it becomes difficult for the flux lines to penetrate through the boundaries. Therefore, if you have more and more grain boundaries, the penetration is difficult. So, HC2 value can be extended further. In addition, if one has precipitates are minute precipitates within the, that means a second phase within the matrix of the primary phase. So, there are these precipitates some isolated particles, very fine particles, and depending on the particle density, depending on the interparticular spacing, once again one can obstruct the penetration of the flux lines. So, all these defects, all these irregularities in the crystalline material can act as pinning centers. So, in most cases it has been taken help of in practical applications or practical devices, whatever wants to make out of these superconducting materials. Both Jc and Hc, Jc is the critical current density above which again a superconducting material changes to a non-superconducting state, and that of course relates to the magnetic field. So, Jc is different for at different magnetic fields. Similarly, Hc is different at different current densities. So, that Hc can increase with the presence of the above pinning centers. So, once again it is the processing which is very important so far as the properties are concerned. We take one example, one particular example of once again a low temperature superconductor. It is niobium 40% titanium alloy with a Tc of 4.2 K. Now, magnetic field strength we have taken for this current density measurement is about 0.9 of Hc2. So, slightly lower, about 10% lower than the Hc2 value, that is the highest value up to which one can expect superconductivity. So, if it is a recrystallized material, recrystallized means again once again a metallurgical term. Recrystallized means a material has been cold worked, that means given a lot of mechanical deformation, significant amount of plastic deformation has already taken place. So, plastic deformation means increasing the dislocation density. So, a cold work material always have a higher dislocation density, but a recrystallized means this dislocation density can be reduced or can be annealed out if the temperature is raised above average recrystallization temperature, or so with increasing temperature more and more energy is given to the system, and therefore, it is easier for the dislocations to move across or move out of the crystals. So, by that process, by recrystallization, actually one reduces the dislocation density. So, there are three kind of situations, three extents of different dislocation density. Recrystallized material has the lowest dislocation density, whereas cold work next one, the cold worked and recovery annealed, that means this is also annealed. So, this is the lowest dislocation density, this is the next lowest, and this is the highest. So, cold worked and precipitation hardened. Cold worked increases the dislocation density, and then precipitation hardened also, in addition one has introduced certain precipitates. So, both together this particular condition, or this particular condition, the material has the largest amount of pinning centers, large number of pinning centers, and this is relatively low density of pinning centers, and this is the least among the three. And accordingly, one can expect the highest current density is here, about 10 to the power 8 ampere per meter square, and then this is slightly lower, 1 order of magnitude lower, 10 to the power 7, and this is much lower, 10 to the power 5. So, just by changing the microstructure, increasing or decreasing the dislocation density, one can vary the current density almost by 3 orders of magnitude. This is quite interesting. Okay. In addition to the intrinsic property of the material, one can actually modify the property to a large extent just by changing the dislocation density or the density of the precipitates. So, this is a very interesting observation, this is very interesting phenomena so far as the low temperature superconductors are concerned. Next, we like to see how the superconductors are fabricated. Normally, since it is basically a current carrying device, one like to have some materials of the superconductors in the form of wires. In case of metallic materials or intermetallic materials, so called low temperature superconductors, all metallurgical processes are used, whether it is melting, casting, then followed by rolling or wire drawing, and so on and so forth. So, all the metallurgical techniques are basically used, although there is a variation in the plasticity or the brittleness of the material. The elemental forms are much softer material, whereas the intermetallic compounds which we have discussed earlier are much brittle material or harder material, but even then one can use the conventional metallurgical techniques to do to make the wire drawing and so on. So, I am not discussing that to a large extent here. On the other hand, let me concentrate on the other fabrication technique, which is a little bit different than the normal metallurgical fabrication techniques. This is for the ceramic superconductors, that is which are known to be brittle materials, and ceramic synthesis, ceramic not only synthesis, but also the fabrication techniques are quite different from the metallurgical techniques. Now, ceramic powders are synthesized by different techniques. The normal powder synthesis techniques can be applied, because it basically starts with different kind of cations, and then you make get them oxidized. So, it can be a soft chemistry route, it can be powder synthesis techniques, solid state synthesis techniques, like if you are talking about yttrium, barium, copper oxide, you can take yttrium oxide, barium oxide and copper oxide, put them together, all of them are powders, mix them together and heat at high temperature, normally in a controlled atmospheric condition. So, that is the powder preparation technique. One can also use sol gel techniques, co-precipitation techniques and combustion techniques and so on to make the powders. So, these are basically available in the powder form, synthesized with right kind of composition, chemical composition, and of course, on the stoichiometry. Stoichiometry is very, very important in case of ceramic superconductors, because almost all of them have certain amount of oxygen deficiency, and that oxygen deficiency has to be controlled very accurately, so that you get the right kind of property. So, sintering under controlled condition with a right kind of oxygen partial pressure is very important. So, you can get different powders, but that is not the end of the story. The powders have to be fabricated in the form of wares. So, ceramic ware fabrication is almost impossible, it is not that easy. So, what the technique is used is called powder in tube technology, or in short the PIT. We take advantage of the flexibility or the plasticity of a particular metal. In this case, the silver. Silver is quite chemically quite compatible with most of the cuprate materials, and at the same time it has the right kind of softness as well as plasticity. So, instead of mixing silver and powders together, which may not have the right the desired property, instead of that, normally what one does is to take a silver tube, a closed end, one enclosed silver tube, and in that you fill the hollow part or inside of the tube is filled up with ceramic powders of the right composition and the right stoichiometry. So, that is compacted as much as possible, and then that silver tube or powder silver tube filled up with the powder is actually wire drawn. Either it can be wire drawn or it can be rolled. So, it can be rolled to make strips, and it can be wire drawn to make wares. So, both the possibilities exist, so that you have a layer of silver outside and the inside is filled up with the ceramic superconductors or ceramic powders. After the rolling or wire drawing, one has to do heat treatment, so that the powders inside get sintered and you have a continuity between the powders. So, with that kind of technique or powder in tube technique is quite useful for making silver filled up with, or silverware filled up with ceramic powders. So, that is the normal structure. That structure of course is not shown here, but I am showing you another structure. This is some kind of a cross section, not the particular single wire. In fact, this is a configuration of a cable. One can say a cable. These are all the cross section of single wires, and so there are large number of wires can be put together and form a cable of much larger diameter. Of course, this particular figure I have shown not only for the ceramic superconductors, but this kind of cross section is also designed for low temperature superconductor or metallic or intermetallic superconductors, which are normally used at lower temperatures. There are some void spaces, white regions, and the darker regions or the colored regions are basically single wires. these have been filled up, in fact they have been put in the matrix of copper, metallic copper. So, all the superconductor cables which are normally fabricated are actually embedded, single strand wires are actually embedded in a matrix of copper. Now, copper of course is not a superconductor, but it is a very good thermal conductivity. So, this kind of system is used so that one can avoid thermal runaway at very high temperatures, at very high current densities. So, current densities of this are extremely high. So, as you can see in the last slide, about 10 to the power 5 to 10 to the power 8 amps per square meter, which is a very high value, and therefore, such high values of current when it is flowing through a cable, if there is a defect in the cable or in the particular wire strand, there is a possibility of a heating up. So, if that kind of situation happens locally the material get transformed from superconducting state to a non-superconducting state, a normal state. So, naturally that will develop a lot of resistance, and at that particular point there will be very high hot spots. So, if such hot spots develop, it is necessary to remove the heat very quickly from that particular zone, and copper being a high thermal conductivity material helps in dissipating the heat from the local region, and that is how saves the cable. So, all the even low temperature superconducting wire strands are actually embedded inside a metal like copper. So, if you are talking about a silver cladded ceramic superconductor, silver also acts as a in the same manner. Silver provides that kind of a thermal conduction which avoids any hot spots or thermal runaway. So, this may however, copper is not the right material in case of ceramic superconductors. It is good so far as the intermetallic or the elemental superconductors are concerned, but in case of ceramic superconductor, copper is not used for obvious reason, because copper is one of the elements present in the ceramic superconductor itself. So, the stoichiometry may get changed, or there will be reaction between the metallic copper and the cuprate superconductors. So, to avoid that, copper is not used, but a more compatible metal silver is used. Silver of course is quite costly than copper, but there is no other alternative. So, if that is one of the disadvantages one can say, but it is not very costly, it is affordable in some depending on the application area, it is certainly affordable. So, a metal, all superconductors either in the powder form or in the wire form, they are embedded in a metallic matrix to avoid local hot spot generation. So, that is why I have shown this particular picture of a typical cable, cross section of a cable, whether it is a low temperature superconductor or a high temperature superconductor. Well, then we come to the most important parts of this discussion is what are the different application of superconductors. We have understood that the superconductor cables or the superconductor material can carry very large currents, and of course, it can also generate a high magnetic field. So, the two most important application of superconducting material is most efficient power transmission. That means, if you are talking about the electrical cables, one can really make miniaturized cables or very small dimensional, small cross section cables to transmit a huge amount of power. In fact, a particular cable of normal dimension can carry almost 1 megawatt of power if necessary. So, this is one area where efficient power transmission can be done. However, it is still not very economic, because one has to understand the superconductivity, the property of superconductivity is available only at very low temperatures. So, you need cryogenic systems. As I forgot to mention one point is most of the low temperature superconductors, the cryogenics is liquid helium. You need liquid helium to cool these materials, where this material becomes superconductor. The boiling point of liquid helium is about 4.2 Kelvin, whereas the boiling point of liquid nitrogen, which is much cheaper, orders of magnitude cheaper, that is around 77 K. So, that was one of the driving force for improving or increasing the ceramic critical temperature of ceramic for superconductors. So, all the low temperature superconductors, if you want to use low temperature superconductors, we need a cryogenic system where liquid helium have to be fed into the system. So, without liquid helium one cannot get a superconductivity of the low temperature superconductors, whereas for high temperature superconductor it is possible to use liquid nitrogen, which is much cheaper, and that was one of the driving force for increasing the temperature. Of course, the ideal is if one can get superconductors at room temperature. So, there is no question of any refrigerant needed to operate the system. So, there is still lot of advantage if one can make use of liquid nitrogen at least as a refrigerant. So, the systems cables have already been designed, and in experimental cables are in use for transmission of very large power from one point to the other. Of course, there is a inbuilt refrigeration system. Then of course, the second more important application is generation of very strong magnetic fields. Well, we have electromagnets. Normally the magnets are prepared by coils, copper coils, and some magnetic materials. But there is a limitation how much magnetic field one can use. That may not be more than 10 Tesla or so. Okay. However, if you need very high magnetic fields, one has to go for superconducting cables, and that is called superconducting magnets. So, one can generate magnetic fields up to 50 Tesla or near more than 50 Tesla, and that is a big advantage. So, in some cases in fact there is no other alternative than to use superconducting magnets. There are certain applications one can think of. So, one can generate or one can transmit huge amount of power through a cable, superconducting cable, and also using such cables or using some wires one can make very high magnetic fields. Miniature electrical generators and transformers. So, most of these things, whatever electromagnetic devices one use, that can be miniaturized, because you are talking about cables carrying very large currents, so and also high magnetic fields. So, therefore, whether it is a transformer or a motor or electrical generator, a dynamo and so on. So, both electrical generators and transformers and even electrical systems like motors can be completely miniaturized to a very large extent, almost 1/10 of the size one can get using superconducting coils. But once again I must mention that the cost is certainly a deterrent, its cost is prohibitive in some cases, and therefore, the applications are to some extent limited. Magnetically levitated transport system. Well, using the Meissner effect, one of the most interesting application of superconductors is the magnetically levitated trains. It has already been demonstrated in a prototype in different parts of the country, particularly advanced countries like Japan and Germany. So, where magnetically levitated trains, that means a train or a transport system which is not resting on the floor, but or on the rail lines, but it is floating in air, okay, because using this magnetic levitation, the Meissner effect, one can float in air a certain amount of weight, because it is a superconducting phase, or superconducting materials are perfectly diamagnetic. So, if there is a magnetic lines of force, it will repel each other. So, by that process one can levitate a very strong magnet over a superconducting material. So, it will just float in air, and therefore, if one can design a transport system with just with little bit of gap between the rail lines, rails and the carriage, and it can move very at a very fast speed, one can reach a speed of 500 kilometers per hour very easily. So, but once again one can design such things, technically it is feasible, but the cost is certainly prohibitive. So, it is still not been commercialized, but demonstration has already been made. There are other effects or other devices which is based on what we call a Josephson junction. The high speed computation with the help of Josephson junction, a very fast switching times, which is a very fast switching time, can also be designed and applied. In fact, the research is still going on to take advantage of these very high switching speeds of the order of 10 picoseconds and so on. I will talk a little bit of Josephson junction in a few minutes, because in addition to the computer application, there are many other applications where one can use, and some of them are already in use. NMR, the nuclear magnetic resonance and nuclear fusion research. For nuclear fusion research is very well connected to the high field magnetic high magnetic fields. Very high magnetic fields are required for nuclear fusion research, where actually the plasma has to be contained within a container, and that is only possible by applying a magnetic field, very high order of magnetic field. So, whenever you have accelerators, nuclear accelerators and accelerators research, you need superconducting magnets of very high magnetic fields, and therefore, one actually uses superconducting magnets. Medical diagnostics is another area where basically NMR technique, nuclear magnetic resonance technique, has been used. It is not only that superconducting materials can be used to make very high magnetic fields, but also it is used to sense very feeble magnetic fields, extremely feeble, extremely weak magnetic fields, and without superconducting devices, such magnetic field or sensing of such magnetic fields is just not possible. So, in the area of medical diagnostic, it has been a very useful technique, and it is already in use. This is an area where in spite of its prohibitive cost, because it is high, it is because of almost essentiality, or no, there is as such there is no other alternative. So, one has the practical application or the commercial application of in the area of magnetic diagnostics. Some of them I will go little bit details. Let us see what next. Yeah, Josephson junction. This is a superconductor junction. I have mentioned that Josephson junction is useful for some of the as a sensor. So, it was discovered by Brian Josephson, and basically it is just like a PN junction or a semiconductor junction. You have two superconductors separated by a small insulating layer. Okay. These kind of junctions are very common in semiconductor physics and semiconductor devices. So, here also like SIS devices, semiconductor insulator semiconductor devices, here it is also SIS super, but S stands for here is superconductors. So, there are two different superconductors separated by a insulating layer, and the charge or the charge carrier can go through this insulating layer through by a so called tunneling process, right. So, that is what is called the Josephson junction. It has many different electronic or very sensitive characteristics, but we will not discuss most of them, except that a junction is to give you little more details of that. The junction is formed by placing a thin insulating layer between two superconductors that I have already mentioned, and well, Cooper pairs I have not introduced so far. When you discuss briefly about the theory, what are the charge species which actually carries the current in this case, and why they do not have any resistance in their path, will come in a minute, how exactly they behave or what is the basic physics behind the transport phenomena here. The Cooper pairs, these are actually known, these are actually the charge carriers in any superconductor. So, these Cooper pairs moves through a insulating barrier layer by a quantum tunneling effect, that is what I was mentioning. So, just like any other tunneling effect superconductors, here also you have a tunneling effect, particularly when there is an insulating layer. Of course, this insulating layer, there is a limit to the thickness, they are primarily in the level of angstroms, and these are all in the thin film form, not in the bulk condition. So, this whole junction is actually just like microelectronics, we have a thin film technology which can be used for making these kind of junctions. Based on this Josephson junction, there is a very important device which has been made and used in practice, that is called SQUIDs, superconducting quantum interference device. Well, from the construction point of view, the design point of view, it is nothing but a double Josephson junction like this. There is forming a ring. These are insulators here. This is one insulating point. This is a Josephson junction, one Josephson junction, and another Josephson junction here. These are superconducting materials, primarily in the thin film form, and then this is another superconductor. So, there is a pair of Josephson junction, and one can give some bias here, and one can find out what is the flux density. Okay. So, one period of voltage variation corresponds to one increase of one flux quantum. So, you can control the flux quantum very precisely, and by that process impact this kind of system, the magnetic field, that means this number of flux lines can be found out. Depending on the number of flux lines passing through this ring, one can find out certain generation of voltage, and that voltage can be generated even with a very small number of fluxes, and therefore, this system or this becomes a sensing device for a very feeble magnetic fields. There is, and this kind of squids magnetometers are available. They are not only used for medical diagnostics, but they are also used for other measurement in physics experiments. So, squid magnetometers are also available for measuring the magnetic characteristics of different materials with very high sensitivity. Now, squids consist of two superconductors separated by thin insulating layers to form parallel Josephson junctions, that has been explained from the particular diagram, and the device may be configured as a magnetometer, which basically measures the magnetic strength or magnetic field strength to detect incredibly small magnetic fields, small enough to measure the magnetic fields in living organisms. Well, in our various organs, we have some magnetic fields, particularly heart and brain, and they have some inbuilt magnetic fields. So, that kind of magnetic field is like this. In our brain, the magnetic field is of the order 10 to the minus 13 Tesla, whereas in heart is about minus 10 Tesla. Now, this kind of feeble magnetic field cannot be measured or sensed other than this kind of squids, okay, based on superconducting materials, and the resolution power of a squid is 10 to the power minus 14, just below that of available in brain. Okay. So, with this kind of a squid system, squid based NMR or superconducting NMRs or Josephson junctions, such kind of magnetic fields can be generated, and that kind of magnetic resonance imaging using squids are available on a commercial basis these days. Obviously, for understandable reason, they are extremely costly. So, this is one very important application of, besides high power and high magnetic field application, at a very low magnetic field also one can use superconductors to detect them. Well, with this we have already discussed different kind of parameters, different experimental parameters which are used for to characterize superconductors, some of the application areas, and some of the very exotic applications like squids, and some of the very important applications like your magnetically levitated transport systems, some of which has not been commercialized, but the technical possibility exists, and whenever we have a room temperature superconductor, maybe some of these things will see the light of will see the light of the day. Okay. With the last few slides, I have just mentioned what is the theory, what is the physics behind it. Well, there is not much scope to discuss the total physics, but I will just give you some glimpses what exactly the physical principles or the physics of the quantum physical theory which can explain the superconducting behavior or the phenomena of superconductivity. So, start with this is called the BCS theory, the Barden-Cooper-Schrieffer theory, more well known as BCS theory. It basically says formation of Cooper pair. Earlier I mentioned about this particular term, the formation of Cooper pair due to electron phonon interaction. So, basically it relates to the free electron and the phonon interaction, which leads to a pair formation, which is a very unusual situation, but at very low temperatures such things can happen. A pair forms, a Cooper pair, what we call the Cooper pairs, 2 electrons comes closer and they are not separated. So, when the charge carrier is not a single electron, but a pair of electrons, and that is usually termed as Cooper pairs. So, the pair moves through the lattice without getting scattered by the lattice vibration. Normally, we have seen in any metallic material, the electrons, the resistance comes from the scattering of the electrons from the atomic vibrations or the phonons, lattice vibrations. But after the formation of a pair, Cooper pair, they do not get scattered. So, that is a very simplified form of how to explain the superconductivity under very low temperature conditions. The force of attraction between the electrons in Cooper pair is stronger than the repulsive force, which is obvious between the electrons. Only when this happens, this is strongly temperature dependent, this phenomena is strongly temperature dependent, and only below Tc such things can happen. The electrons, a pair of electrons, instead of having a repulsive interaction, they have a attractive interaction, and that is a special case of the electron phonon interaction, and that is a very simplified form of BCS theory. However, such theories have been questioned when there is a discovery of high Tc superconductors. Okay. In high Tc superconductor, we are talking about high temperature. So, what happens in low temperature may not happen in high temperature, and therefore, there is a question mark of the applicability of the BCS theory in the ceramic superconductors. And immediately after the discovery of ceramic superconductor, there are many physicists, the well known physicists have started working on it, and they have proposed many different theories. I am once again not going to the details of that, it will take long time. So, we will just mention some of them. These are not the complete list, but there are all possible theories. One is called the resonating valency bond theory, spin fluctuation theory, anisotropic phonons theory, bipolarons. These are in fact, these two are more important, the resonating valency bond theory as well as the bipolaron theory, excitons theory, BCS crossover theory, plasmons, spin liquids. So, there are many aspects of these. Once again, I am not going to the details of that, except that just mentioning that BCS theory, which has been applied very well to the low temperature superconductors, is not quite accepted by the physicists for the explanation of the high Tc superconductors, and still research is going on. Many propositions and hypotheses are being put forward, and I am sure in future some unanimous decision or unanimous acceptance will come. That is all so far as the theory is concerned. I will not go to the details of that. I forgot to mention two important parameters in addition to whatever we have already discussed. Arising from the theoretical and experimental investigations, these are length parameters, which is characteristics of some of the superconducting materials. Superconductors, there are two characteristics lengths. One is called the London penetration depth, and other is coherence length. So, these are the two also the length parameters which characterizes different behavior, different characteristics of superconductors. I will just make a definition of that. The London penetration length is the London penetration depth refers to the exponential decaying of the magnetic field, actually of the magnetic field at a surface of a superconductivity superconductor. It is related to the density of superconducting electrons in the material, okay, the superconducting electrons in the material. Okay. Of course, one has to remember that in a superconductor, low Tc superconductor, it is primarily the electrons, the free electrons or the pair of such electrons actually charge carrying species, but in high Tc superconductors there are not free electrons, there are more localized electrons. So, we talk about polarons or excitons and so on. So, that has been already discussed earlier. It is the penetration depth. So, how long particularly when we are talking about the fluxes are repelled by the superconducting material, but the fluxes we can penetrate to some extent, it is up in the surface. So, not exactly like a mirror plane that it gets reflected, but it gets penetrated to some extent and then comes back. So, that is one of the characteristic length of what we called the penetration length. And another is also important to study the characteristics. This is called coherence length. So, it is related to the Fermi velocity for the material and the energy gap associated with the condensation to the superconducting state. So, it has to do with the fact that the superconducting electron density cannot change quickly, because if there is a superconductor and non superconducting state, that are normal state coexisting together. So, suddenly there will be a boundary. So, there is a boundary and that boundary has a finite length. So, between the superconducting and the non superconducting zone there is a finite length, and that is the characteristics of the coherence lengths. So, that is what has been mentioned there, that the minimum length over which a given change can be made lest it destroy the superconducting state. For example, a transition from a superconducting state to a normal state will have a transition layer of finite thickness, which is related to the coherence length. So, this is to some extent related to the domain boundary, thickness of the domain boundary either in ferroelectrics or ferromagnetic material. So, there is no sudden change because it needs certain amount of thickness within which a gradual change takes place from a superconducting state to a normal state. So, that is what we call the coherence lengths. Now, these length parameters are important from the point of view how to design the material, how to enhance the properties, how to particularly by when you are talking about a granular superconductor, how to increase the Hc2 value. We have talked about pinning centers by dislocations, grain boundaries, precipitates, but it can also, the nature of the grain boundary is also important to enhance these properties. So, coherence length, a idea of coherence length is important to understand and design or modify the properties of the superconductors. So, with this more or less we have come to the end of the discussion. Lastly, I will give you this is the penetration depth and this is the coherent length of few superconductors like tin, aluminum, lead, cadmium, niobium and so on. These are the length scales, the coherence lengths and in the nanometers, and these are the penetration. So, a material like aluminum, the depth of penetration is much larger compared to this kind of which is not a superconductor, but for the superconductors is much smaller. Okay. So, niobium, lead and tin they are actually much smaller penetration depth, whereas aluminum and cadmium the penetration depth is much larger. So, for any superconductors this applies, the penetration depth is much smaller, whereas for the coherence length here is like this. Okay. Lastly, the last slide I believe, sorry, this the title came later. I will just try to mention that there are large number of Nobel Prizes has been awarded in this area, and started from Campbell Owens and as late as 2003. So, almost 90 years, over the 90 years, several Nobel Prizes have been awarded on the superconducting area, the physics of superconductors. Still many things need to be understood, and I hope many more Nobel Prizes may have to be awarded, because the subject is still unknown to a large extent, and much more complex physics is there than we have understood so far. However, the material is very important and it is very unique material, it is on the extreme end in the conductivity scale, and therefore, it is of tremendous technological importance, and possibly one day it will be cheaper and more commercial applications will come by. Well, with this let me complete the discussion on superconductivity, and thank you for your attention.